Welcome from Nexus. So, we're diving into your part of 10 section today. It's a really strong recap. Best practices, the do's and don'ts, key resources for big data.
Yeah, it's comprehensive. What we want to do now is maybe sharpen the focus a bit, especially for that computer science audience you're targeting.
Exactly. Look at the architectural underpinnings. Less what, more why, technically speaking.
Precisely. How the architecture really dictates these best practices.
Okay, let's start with that first point you make about analytic approaches. Your advice. Don't rely on a single approach to big data analytics. Good advice. But we think it could be strengthened by getting more specific about the technical constraints.
Right. The weakness we saw is that while you correctly warn against, say, using MapReduce for everything,
Which is spot on.
the alternatives you list, like text analytics, streaming, predictive, they're a bit too general. It doesn't quite nail down why a batch system fundamentally fails for real-time stuff.
Yeah, it's missing that sharp distinction, isn't it? Between a batch model and, like, a continuous real-time model. It's all about throughput versus latency, fundamentally.
Mm-hmm. MapReduce is built for throughput, chewing through massive data sets.
But it's not built for speed of decision, not for low latency.
So the suggestion here is maybe reframe that don't. Focus it squarely on matching the problem's time needs, its temporal characteristics, with the right compute paradigm.
Make it clear why batch frameworks hit a wall when things need to happen fast.
Exactly. Align the business need, the latency requirement, with the architecture.
Okay, so let's get concrete. Instead of just saying, hey, streaming data is important,
Which it is.
of course, but provide that architectural context. Say, okay, if you need immediate action based on event sequence like real-time fraud detection.
Yeah, or maybe like live anomaly scoring on sensor data.
Right. You just can't wait for a batch job to run overnight.
That's where you need to explicitly point the reader towards, say, complex event processing, CEP.
Or systems like Esper, maybe, using rules engines.
Precisely. Things that trigger actions instantly when a pattern hits. Their performance is measured in milliseconds, not hours.
And then contrast that directly. Say, look, MapReduce, that's for batch aggregation, after the data's landed. Different world.
If your goal is a daily report, fine, MapReduce works.
But if it's stopping fraud now, using that batch system just isn't technically feasible. Making that explicit changes it from just good advice to real architectural guidance.
Well put. Okay.
Moving on. That idea of architectural needs leads nicely into the resources section. Specialized problems often need specialized tools, right? Particularly open source ones.
Mm-hmm.
So your next point, the listing of 10 great big data resources in Chapter 24, while comprehensive for commercial offerings, misses an opportunity to emphasize foundational open source projects that drive architectural flexibility necessary for specialized data management.
Yeah, we noticed the list leans, pretty heavily towards standards bodies, NIST, OASS, and the big vendors, IBM, Google, Amazon.
Which are important resources, no doubt.
Absolutely. But for a CS pro who might be actually building a stack, a custom one, it feels like it's missing some key open source building blocks, the things that really enable flexibility.
So the weakness is, by maybe over-indexing on the big players, it doesn't fully empower the reader to implement that polyglot persistence idea you talk about elsewhere, handling all that data variety.
Exactly. You need the right tools for the right data shape.
Uh-huh.
So the suggestion is pretty straightforward. Enhance that resource list. Call out specific open source projects that offer that extensibility, that support for specialized data types.
And that reinforces your other point about planning for consistent metadata, too.
Right. It gives the reader the actual components they might use to build that kind of tailored mixed architecture.
Okay, examples. Let's be specific. We think you should definitely highlight the Postgres community.
Oh, absolutely. It's more than just a solid relational database.
Its extensibility is the key thing here, isn't it, in a big data context?
Totally. Because you can add new data types, new operators, even custom indexing. That makes it super adaptable.
So it can anchor a diverse setup, handling some relational needs, but maybe in a more flexible way.
Exactly. It can be a really strong foundation, especially where you need custom operations or schema evolution isn't, totally locked down.
Good point. But polyglot means more than just SQL, even extensible SQL. So what about non-relational? Why specifically call out something like, say, Neo4j?
Because it tackles a whole different kind of problem structure.
graphs, highly connected data.
Like social networks or maybe recommendation engines?
Perfect examples. Or complex classifications, things where relationships are the core data. Traditional databases, even Postgres, aren't really optimized for traversing those connections at scale. Neo4j is built for that specific niche.
So it's about highlighting the specialized tool for a specific data structure need.
You got it. And then for another common pattern, maybe something like React?
For the key value needs, massive scale KVP.
Right. Think session stores, user profiles, caching huge amounts of, maybe unstructured objects. React is designed for that kind of high availability, high scalability, key value workload.
Okay, so listing those three, Postgres for extensible SQL, Neo4j for graphs, React for KVP, gives really concrete starting points.
Yeah, it moves beyond just vendor portals and gives actionable open source options for building those flexible modern persistence layers.
Makes sense. Okay, final area, security. Always critical, especially when data is spread out everywhere.
Definitely a big one.
Your point. The crucial advice in Chapter 25, don't forget to manage data securely, should be framed around the unique governance risks posed by the high-volume, physically distributed nature of the big data infrastructure itself, contrasting it sharply with traditional data stores.
So the current advice, it talks about privacy, securing data, which is necessary, obviously.
Standard stuff.
But it feels a bit generalized. It doesn't quite hammer home the new risks that come specifically from moving away from, say, a centralized RDBMS with strong ACID guarantees.
Right. The moment you distribute data across potentially hundreds or thousands of commodity nodes for scale.
Like an HDFS.
You inherently change the security game. Sensitive data, PII, PHI, it's now deliberately copied across multiple machines that might not all be equally secure. That replication, which is there for fault tolerance, fundamentally multiplies your exposure surface. That's the core issue.
And that's the weakness, right? The advice doesn't stress that specific architectural vulnerability enough. Traditional security thinking isn't quite sufficient.
Precisely. So the suggestion has to be really pointed. You must implement security protocols way earlier, before the data even hits the distributed system.
You need to tackle how to secure data that you know is going to exist in multiple copies, across who knows how many nodes.
Because HDFS is built on that replication, right? If you've got a replication factor of 3, which is common, your risk for that data block potentially being exposed is tripled, at least. One vulnerable node compromises 3 copies.
Exactly. So the really actionable suggestion is to push for techniques like tokenization or maybe data anonymization much earlier in the process. Make it part of ETL, part of data prep.
Mask the sensitive stuff before it enters HDFS.
Yes, that's the key. Ensure PII or whatever's sensitive is obscured before it gets replicated across the cluster.
But hang on, there's a trade-off there surely. If you tokenize or anonymize that early, doesn't that potentially limit what kind of analysis you can do later? You lose context.
That is the fundamental trade-off, and that's why this needs explicit discussion. You have to decide up front what level of data fidelity is truly needed for the planned analyses versus the security risk.
So if you absolutely need the raw PII for some specific query,
Then you're into much heavier territory. Encrypted storage, maybe homomorphic encryption in some cases, complex access controls. It gets way more complicated and usually slower.
okay, so the practical advice, the suggestion, is really about making a conscious choice. For most big data analytics, masking that PII early via tokenization is probably the most pragmatic route.
It's the most direct way to mitigate that risk inherent in the replicated HDFS architecture. Secure it at the source, because you can't easily secure every single node it might land on later.
Got it. That makes the security advice much more specific to the realities of distributed systems.
Exactly.
All right, well, that wraps up our look at the part of tens. We've touched on linking data velocity to architecture choices more tightly, beefing up the resource list with key open source tools for flexibility, and making sure the security advice really confronts those distributed systems risks head on.
Yeah, so just to recap the action items. 1, clarify that technical split between batch, like MapReduce, and real-time, like CEP, really focusing on latency versus throughput needs.
2. Add specific extensible open source platforms, Postgres, Neo4j, React were our examples, to guide readers towards building those polyglot persistent strategies.
And 3?
And 3, emphasize securing sensitive data early, tokenization or anonymization during ETL before it hits HDFS to manage that replication risk.
Just some thoughts, obviously, but we think focusing on these areas will make this section even more valuable for your technical audience.
Absolutely. Feel free to revise and send it back our way if you'd like another look. We're happy to help.